Now, our next speaker is Marisa Kirisame, and Marisa's at Utah, and I just want to put a plug in for Marisa, who's nearing graduation, and so will be on the market soon. So go have a chat with Marisa after the talk if you're looking to hire someone. And Marisa's going to be speaking about spineless traversal for layout invalidation. Over to you, Marisa.
Hi. So let's open a web page. Let's say we're opening Google. Then what happens is the browser has undergoes a long and complex pipeline to convert this HTML DOM tree to pixels on the screen. This pipeline includes JavaScript execution and garbage collection, CSS matching and styling, and layout and rendering to convert it from the tree to pixels. Now, what happens when the user clicks a button on the web page? Then the corresponding JavaScript will be executed, modifying the HTML tree. Now what we compute is now stale, and we have to recompute them again. One sec. Because the web browser wants to keep a smooth user experience of 60 FPS, and because layout is only a tiny part of this pipeline, this means layout typically get a budget of 1 millisecond. On this tight budget, every cycles matter. So how does browser deal with this huge computational demand? Two tricks: incrementalization and amortization. In particular, this means that when the tree is changed, the browser don't immediately recompute the layout. Instead, the browser merely marks what is affected by the change with a dirty bit. Only later on, when this layout is requested, do the browser go find all dirty nodes and fix them in one go. So with this add of incrementalization and amortization, this incremental layout is 100x faster than from scratch layout. So this is a pretty critical optimizations. So let's see how this algorithm works in more detail. In here, let's say we have a single node that's dirty, the red node. Then this algorithm has to go find that red node and fix it. But by recomputing the node, note that this fixing itself also counts as changing the tree. So now its dependency is dirtied. And we have this cat and mice game again. Now let's say this time, when we are recomputing this node, it's the same. We doesn't change anything. Then everything is good. We don't have to dirty the dependency, and we can stop here. This stopping is important because with it, typically for each external dirty node, we only have to do like 3 to 5 recomputation to fix everything. So that's how the algorithm works. To sum up, it has 3 parts. It has to find all dirty nodes. It has to recompute them and dirtying all their dependency. Now this runs in a loop until all dirty node is resolved. Now a lot of prior work has focused on the other 2 parts, recomputing node and dirtying them. For this talk, we want to focus on finding dirty node as fast as possible. Let's see what the state-of-the-art do. So this is the state-of-the-art algorithm trying to find this red node in the bottom. To find this node, the state-of-the-art algorithm traverses the tree top-down, touching all orange node. Now this orange node we call auxiliary node because we touch them only to find the red node, not to recompute them. As you can see, we are touching about 20 to 30 auxiliary nodes, and each of them is an L2 cache misses. This means we are paying 1,000 cycles just to find the red node. And the computation of the red node is typically not 100,000 cycles. So in here, we have an von Neumann bottleneck-like situation where we are spending more time finding out what to compute rather than computing it. So here's our solution. What if we just don't traverse the tree? Instead, we use a queue to store pointers to the node that is dirtied. Then we have a similar loop. For each element in the queue, we dequeued them, we computing them, and enqueuing their dependency, which is newly dirtied. We execute this loop until the queue is empty. Then no more things is dirtied, and we are done. So let's look at this example here. In here, we have a single dirty node. Now, this dirty node is in this queue. Now, processing that doesn't touch any other node. We just jump directly according to the pointer. Then, its dependency is also enqueued. Again, we jump directly to this node. Now, this time, maybe we are dirtying its two dependency. They are both enqueued. And then we are going to process them one by one. For this case, let's say processing it does not change the tree. Then we are done. Now the queue is empty, so this process ends here. Okay, we are talking about this queue. Does it matter what order do we insert element in the queue? And does it matter what element, like they're processed? For correctness reason, it turns out no. Any order is good as long as the queue eventually gets cleared. But yes, for performance reason. So let's look at this example here, where we have a tiny tree of 3 nodes. The left node is dirtied. Processing it will include its two dependency. Then let's say we are processing the top dependency first, and the right dependency later. Now, this right dependency may include the top dependency again. Then, what this means is the top node is included and processed twice. This is bad because we are doing extra work. So what can we do? We can try to make this queue clearing process the same order as if we are doing a from scratch layout. Now, this must work, because a from scratch layout only touch every node once. So to implement this from scratch layout, what we can do is we can tag each node with a timestamp. Then this timestamp is assigned when the node is finished computing initially. And this timestamp increases monotonically. Then we can index our queue with this timestamp. Let's see how it is implemented and its performance characteristic. In your implementation, main heap, we are using a main heap on a pack and a flat array. Because we typically have less than 100 nodes, this means the whole priority queue is in cache. Then the bottleneck comes from the invocation to the comparison function. Now, the queue is 100 nodes, so that translates to 8 comparisons per push or pop. And because each comparison is 5 cycles, the total time per push pop is 40 cycles, which is a single L2 cache misses. This means as long as the baseline state-of-the-art algorithm have a single auxiliary node for each dirty node, we are already on equal ground. In real life, the state-of-the-art algorithm has much more auxiliary nodes, so this means we are winning in real life. Okay, so what should this timestamp be? It turns out it can't be a usual 64-bit integer. Here's why. Let's say we have a tree of 3 nodes again. The left node have a timestamp of 4. The right node have a timestamp of 6. Then let's say we want to insert a node in the middle. What should its timestamp be? It has to be greater than 4 and smaller than 6. So that's only 5. Let's try to insert again, and this time we are out of gap. So we need something other than an integer timestamp. It turns out the algorithm people have come up with this idea of order maintenance, which presents the idea of infinitely splittable time. It provides two APIs exactly what we need: comparison and insertion. It is critical that both of them are O1 with a small constant of typically dozens of cycles. Comparison is the critical operation because a single node is inserted once and compared many times. So let's see how we can optimize comparison. The implementation of comparison is as follows. It takes two pointers, A and B, and it computes 4 timestamps. The 4 timestamp. Finally, it lexicographically compares the two up timestamp, then the two down timestamp. As you can see, this code has two bottlenecks. One is that we are doing pointer access on here, and each of them is potential L2 cache misses. Another is we are having an unpredictable branch. This unpredictable branch will cause pipeline stall, which is about 20 to 30 cycles on a modern CPU. So to solve the first problem, what we do is we use a custom allocator, packing all timestamp tightly, packing all nodes tightly. Then, moreover, since the nodes are packed tightly, we can now use pointer compression, so each node is only half its original size. Now, per cache line, we are fitting 4x more objects. Then, to solve this unpredictable branch problem, we Sure, good. We eliminate this unpredictable branch. Instead, we are gonna use handwrite assembly to use conditional move. Now, this whole comparison is about 5 cycles. So to sum up, the problem of incremental web layout is they are gonna have too much auxiliary node and suffer the von Neumann bottleneck. We solve this problem by using a queue to store the dirty node, and this queue is indexed by all the maintenance timestamp. Now let's see how it works. We evaluate our algorithm, Spineless Traversal, over the baseline algorithm on 50 websites. These 50 websites are what you and me use, like Google, Twitter, GitHub, Lichess. We modify Ladybird, a web browser, so that every time it tries to lay out, it prints out the HTML DOM tree. Then we compute a diff of between these DOM trees, and we fit the diffs into our baseline algorithm and our algorithms. The result is plotted here. We have 2,200 points, and each frame is a data point in the scatter plot. The plot looks like this. Most point is below this x equal y black line. This means for most point, we are winning. Let's break down this plot down. Overall, it is a 1.8x geo-mean speedup. As you can see, this plot is made up of two kinds of points, one on the top right quadrant and one on the bottom left quadrant. On the top right, what happened is an initial load frame where the browser just finished network loading and is presenting a huge diff for the incremental algorithm to handle. In such case, we are paying the extra cost of creating all the maintenance node, so we are a bit slower. But in this case, the user is already waiting for the network load anyway. For the small frames, they are what we call a forced layout. This means that multiple small changes is done inside a single 16 millisecond time frame, and each of them must be laid out separately. So the small frames come in group, and they must be handled quickly. So all in all, this is a 1.8x geo-mean speedup on the more important part of this whole data set. We are talking about incremental web layout, but what we have done instead is I've built a general framework This framework works with different kind of place where we have dirty bits, or we can use incremental evaluation. For example, we have modified our approach to work for type checking in IDs and structural editors. See our upcoming paper in Uppsala. It also works for, like, let's say, parsing, compiler, just anything attribute grammar. So if you're interested, get in touch. Any questions?
Thanks a lot. It was really, really interesting. I really like this. So I just want to know about basically memory footprints of this, because I think you are using some additional memory to compensate the computations.
Yes. Absolutely. The extra memory footprint we use is this order maintenance object. This means for every node in a tree, we are using about 128 more bits of memory. This is not that much because each node in web layout typically is like 1,000 bit of, it's like 1,000 byte of memory. So this is like a few percentage more overhead, but it may differ from different applications.
Okay, so you said that it may differ, but it is proportional to what factors? What factor basically?
It's not a factor, it's a constant of like 128 bits.
Okay, I see.
It's time for another question if we have one. I've got a question. Could you just say a little bit about the applicability or the difficulty of transferring this into other browsers? You evaluated in Ladybird. And I know that browsers are very, very complex things. Can you just say a little bit about that?
Yes. In fact, what we do is we build a custom DSL, a custom compiler, and evaluate our algorithms on that custom DSL. So we didn't really evaluate it inside Ladybird. The problem with web browsers is that they are like, the layout part is like hundreds of thousands lines of code, and it's gonna be really difficult to swap in a replacement.
Great, thanks. Let's thank Marisa for a great talk.